How you doing? I'm Mr. Rose, and today we're going to talk a little bit about momentum, specifically conservation of momentum. Now here I have a problem all written out that we're going to go through, and as always, I recommend that you read the entire problem, try and solve it before you watch me actually go to do it. It should be a relatively straightforward application of conservation of momentum. Before we get into that, I just want to give a little bit of background and make sure we're all on the same page. Now we should know that momentum is essentially moving inertia. In other words, it's an object's ability to continue to stay in motion or to remain in motion. We all know Newton's second law, F equals ma, and at this point we should be comfortable knowing that Newton's second law is really a momentum law more than that F equals ma. Now, when we talk about conservation laws, we know a whole lot about conservation of energy at this point. Energy before something happens is equal to the energy after something happens. Specifically, we're talking about conservative forces. If we have non-conservative forces, obviously, then we need to include the energy lost to the system. Now, one of my favorite sayings is conservation of momentum and conservation of energy both always work. But in order to use conservation of energy, you need to be a little bit of a better accountant than conservation of momentum. Now, what I mean by that is we lose some energy to the system that's usually hard to find. Now, with momentum being a vector quantity, a lot of students find that conservation of momentum is a little bit more challenging. However, it is much more straightforward, and unlike the exponential of kinetic energy, momentum is just pure momentum, mass times velocity, no matter how you cut it. The only thing you need to do is be aware that that momentum is a vector quantity. So we need to make sure that we're keeping I hat, j hat, k hat notation, or we're keeping things in sines, cosines, and tangents, making sure that we know the direction, positives, and negatives that we have. So this is going to be another instance where if you don't start with a coordinate system, that may end up to bite you in the behind. Now, again, this is a conservation problem, and I've spoken a little bit about conservation of momentum. Essentially, there are three types of interactions with conservation of momentum. We're going to start with what I believe is the most straightforward, what I call an explosion, and, well, what most every physics teacher talks as of an explosion. Now, an explosion is basically a reverse inelastic collision. Well, what does that mean? An explosion is when you have one object doing something. It could be a rest, it could be moving, it doesn't really matter. And that one object, something happens, that's the explosion part, and it ends up as multiple objects. Introductory physics, we usually have one object that explodes perfectly into two pieces that are going exactly opposite each other, 180 degrees from each other. The problem I have out here, this is a little bit more complicated, but again, very, very straightforward. An inelastic collision now is an object that multiple objects, more than one, that come together and stick, which is why I say the explosion is like a reverse inelastic collision or vice versa. And then there's an elastic collision, and an elastic collision is when two objects, or more objects than that rather, collide and bounce off each other. Now, one other thing to keep in mind, and we'll get to this later on, with an inelastic and an elastic collision, a perfectly elastic collision means energy is 100% conserved. An inelastic collision, energy, again, still has to be conserved into the system, but the energy of the objects is not conserved because we lose energy to things like heat, sound, friction, again, work done by non-conservative forces. So, now let's get to our problem and a brief overview. Again, aside from being a physics student, you are like this super secret agent, and you find this ticking package on some frictionless surface, so it was on some ice. You know, it's New England, maybe you were ice skating, it's getting kind of cold, and in order to save the day, you throw that object away. Now, as some passerby comes by, or you have to fill out your Watertown police report, we need to know exactly how fast you threw that object. So that's what we're going to solve here. So the first thing I'm going to do, like I said, is I'm going to designate a coordinate system in my x and my y. Now, next, I'm going to sketch just the scenario of what's going to happen. I'm going to have my initial mass, m0, that would be my 4 kilogram object, and I'm going to give it some random initial velocity, v0. Now, even though I have this going in the x direction, I don't actually know this. This is arbitrary. When I end up solving for my final velocity, I'll know exactly that direction. Again, because momentum is a vector, but I need to start somewhere. So this is just a very arbitrary initial system. Then there's some kind of explosion. Big boom. And what happens next is my object is now going in two directions. I have one piece that I'll just call M1 going due north. And that is going due north at 3 meters per second. And I have a second piece. I can call that M2 going, I guess M2 should be down there actually. And that is traveling at 5 meters per second. 5 meters per second at 30 degrees to the horizontal. So, or 30 degrees north of east, as I have written. So, to look at this situation, I'm going to really examine the before and the after. And I know by conservation principles, all of my momentum here has to equal the total or all of my momentum there after that explosion. That's what we're trying to figure out. So, because momentum is a vector, I believe the easiest way to tackle this problem is going to be able to keep things in I, J, and K notation. So the initial momentum is easy. My initial momentum, well, that's just momentum equals mass times velocity. And in reality, I'm kind of stuck here. I can put in my momentum. I should have an initial there. I should have some vectors. There we go. My initial momentum is essentially my 4 kilogram mass, 4.0 kilograms times V naught. And at this point, I can't do anything with that. I'm going to have to come back to that sucker later. Now, my final momentum, want that so I can see, I'll bring that back if we need it. My final momentum has two different pieces. Redraw my problem here. I've got M1 traveling at some velocity that was given. And I have, again, mass number 2 traveling at 30 degrees to the horizontal at V2. So these two pieces make up my total momentum after that thing collides. So I want to know my momentum final. Well, my momentum final is going to be mass 1 times velocity 1 plus mass 2 times velocity 2. And again, I think it's going to be easiest to keep this in IJK notation right now. So mass 1 is easy because that's just going due north. And as we know, due north should be the J hat direction. So the momentum of object 1 is equal to my perfect, I'll just keep it actually in terms of variables, M1 now times V1 in the J hat direction. That is going to be, I said it was 2.0 kilograms, and it was traveling at 3.0 meters per second in the J hat direction. So the momentum of object 1 after the collision is just 6 kilograms times meters per second in the J hat direction. That's pretty straightforward. My momentum of object 2 now is M2V2, but V has component velocities. It's got a I hat and a J hat velocity. So my momentum 2 is really equal to M2 times V in the I hat plus V in the J hat direction. So in order to calculate that, again, this is not going to be hard, nothing we haven't done before. Momentum 2 is equal to, well, let's see, this I hat direction is going to be a factor of cosine, right? So I'm going to say it's M2 times V2 is 5 meters per second, 5.0 meters per second, times the cosine of 30 degrees, and that is in my I hat direction, plus 5 meters per second times the sine, it looks like I'm running out of room on my paper, sine of 30 degrees, and that should be in my j hat direction. So this is, again, fairly straightforward, and not that I memorize these very often, but we use sine 30, cosine 30 so often. And, oh, wait, looks like, oh, M2, there we go. I need the parentheses there. All right, so M2 I know is 2, so 2 times 5 is 10. 10 times the cosine of 30. We should we should be fairly confident with that to say that my momentum 2 is going to be equal to 8.66. That's going to be kilograms times meters per second into the I hat direction, right? That's 2 times 5 is 10. 10 times the cosine of 30. Cosine of 30 is 0.8660. Plus, again, m times 2 is 10 times sine 30. So that's going to be plus 5 kilograms times meters per second in the j hat direction. Now, this combined momentum 1 and momentum 2, those are both in my pieces after my collision. So now my final equation, momentum before the thing exploded to the momentum after it exploded, that is just going to be what we got before. Let me pull that back down, right? What we got before here is just 4 times V naught. So I've got 4.0 times V0 kilograms times meters per second is equal to the total momentum after these things collided. 6.0 kilograms meters per second j hat plus 8.66 kilograms times meters per second I hat plus 5 kilograms, that should be 5.0, meters per second in the j hat direction. Combine my directions, I have 4.0 V naught kg meters per second equals 8.66 I hat plus 11 j hat kilograms times meters per second. And now I've got a little bit of an option here. This is almost my final answer. I have 2 options. First, I'm going to keep this again in IJK notation because I think that is the easiest, and that keeps my vector notation. I just need to grab my calculator. We can divide the 4 straight through. So I have a V0 equal to 8.66 divided by 4 is 2.165. 2.165. That is in the I hat direction. Plus 11 over 4 is 2.75. 2.75 in the j hat direction. And that whole thing is in meters per second. That is my final velocity. That answers my question. That is my final velocity and the direction because I gave it in vector notation. Exactly what we're looking for. Now, if the question specifically asked what is the magnitude and the direction of the velocity, I wouldn't have gone this way. From here, I can solve it anyway. It's not like I changed anything, but I would go back to where I started up here. If I wanted the specific magnitude and direction, right, I would start from my 4 V naught equals 8.66 plus 11, and I know I had j hat direction, sorry. Just even write that in. If I wanted the magnitude and direction, well, then I'm going to take the square root, the Pythagorean theorem, the square root of my squareds of 8.66 and 11, and then divide that whole thing by 4. I can do that in one step. I could say V naught is equal to, put my vector, the square root of 8.66 over 4 squared plus 11 over 4 squared. Oh, there we go. Let's see, the square root. 8.66 over 4 to the second. Plus 11 over 4 squared. 3.49996. So that's going to be about 3.5 meters per second. Now we need the direction, obviously. So again, I could have used that, and even though you just heard me say on my calculator, I didn't, because this would be an extra step. I want to go from there. My direction, if I went from here or here, it doesn't matter. I'm in the I hat and the j hat direction, so I, j. That means my initial velocity vector is somewhere over there. I'm actually now solving for this little angle. So we can see that I have an x and a y, so I'm going to use 10. So find my angle, I'm going to say the inverse tan of I over j, 11, j over I, sorry. Yep, 11 over 8.66 verse tan of 11 over 8.66, 51.78. So that is at 51.78, or I guess if we're having sig figs, 51.8 degrees, I would say north of east, or simply above the horizontal. So this would also be a final acceptable answer. Again, depending on how the question is worded, if I just wanted the velocity, this gives the velocity and the direction, vector notation. If I want the magnitude and direction, then I get the magnitude 3.5 meters per second and the direction 51.8 degrees north of east or above the horizontal. All of this is possible because of conservation of momentum. It is plausible that you could attack this problem with conservation of energy. I wouldn't recommend it. It's going to be much more difficult. If I add friction into that, it becomes even more difficult. So again, conservation of momentum is a huge concept that we can do a lot with. We're going to end up combining a lot of our conservation laws, using conservation of energy and momentum simultaneously. This is just our first interaction, our first stab at conservation of momentum. And again, I believe that the explosion, so to speak, is the easiest of the bunch to start with. That's all I have for you today. Please feel free to like, comment, and subscribe if you're watching this on my YouTube channel. I say click a lot. I may have even mentioned this before. I don't even know what that means. But comment, subscribe, that's important. Give me a thumbs up. And that's all I have for you. You will see me next time. Have a good one.